Hi there and welcome to Trigonometries. Today we're going to solve some problems from our college algebra course on basic functions and their graphs. The first problem uses some of the ideas from this section into a word problem about real life data. The table here shows the life expectancy of a child at birth in the United States from the years 1930 to 2010. We find this information from the CDC. A model for the life expectancy during this period could be given by y equals 60.1 plus 0.356 times t minus 0.00162 times t squared, where t is measured as years from 1930. So its range would be 0 to 80 on this table, where 0 is the year 1930 and 80 is the year 2010. We have three questions about this data that we want to answer, and we'll do them one at a time. The first is, what does the y-intercept of the graph of this model represent? Okay, so I've written up on the board the model that we were given, with t being the time in years since 1930. So again, we have y equals 60.1 plus 0.356 times t minus 0.00162 times t squared. The first question that we were asked is, what does the y-intercept of this model mean? Well, the y-intercept of this model, just to write down what it is what happens when t is equal to 0. Because if you were to graph this on a plane that has y as on the y-axis and t on the horizontal axis, then y equals 0 is the point where it crosses the y-axis, and that's why we call it the y-intercept. And so this point here for this guy would be 60.1 plus 0.356 times 0 minus 0.00162 times 0 squared. Both of these terms being multiplied by 0 are gone, and so the y-intercept would just end up being 60.1. In order to figure out what this means, we have to remember what our variables are. Now, t is the time in years since 1930, but y is equal to the life expectancy at birth in year t. So somebody born in that particular year, what would be their life expectancy? So this here would be the life expectancy of someone born in t equals 0. But t equals 0 is the year 1930. So this should be the life expectancy, or rather it approximates the life expectancy of someone born in 1930. Looking at the table, the actual value of that life expectancy is 59.7. The reason for the discrepancy is that this is a model that approximates the value of the life expectancy at each year, so that we have a chance to kind of see the relationship between the time in years since 1930 and the actual change in the life expectancy. The next question is to determine the life expectancy in 1948. Well, the life expectancy in 1948, since it's not given in the table, the only way we can get it is to approximate it with the model. Y here is the life expectancy at birth in year t. T is the time in years since 1930. If we want to use this model to approximate the life expectancy in 1948, we have to first find the t value that corresponds to 1948. Since the t value is the time in years since 1930, we need to find out how many years since 1930 that 1948 was. To do that, we simply subtract the value of 1930 from the value of 1948, and that'll give us how many years elapsed between those two, or the difference of years in that time frame. So our t value here is going to be the 1948 year minus the 1930 year, which produces 18 years. So 1948 is 18 years from 1930, and so that's why the t value will be 18. So to find the life expectancy then, we simply have to plug 18 into this function here, and we get that y of 18 is equal to 60.1 plus 0.356 times 18 minus 0.00162 times 18 squared. So to figure this out, you're going to need to plug this into a calculator in order to solve it. So let's pull out our trusty calculators. Now mine is a very old school TI-89 that I have had since I was in high school. Plugging it into my calculator here, I get 65.98, which means that the life expectancy after 18 years, y of 18, is approximately equal to 65.98. But if you look, all of these guys here are given in sort of 3 significant digits. So we really ought to give our answer here in 3 significant digits, which requires us to round a little bit. We want to round really to this point here, but if we round the 8 up, that'll make this a 10, which actually forces us to round that up. And so this rounded to 3 significant digits is 66.0. And that's the approximate life expectancy in 1948 according to this model here. The last question for this problem is we want to use this model to estimate the life expectancy at birth in 2020. To use this model to estimate the life expectancy of someone born in 2020, all we have to do is plug in the t-value that corresponds to 2020 into this t-value here. Well, remember, t is the time in years since 1930. So to find the t-value for 2020, just like before, we have to subtract 1930 from 2020, which would produce a value of 90. So that value there, we're now going to plug into the model to figure out what the model says should have happened in 2020. So this will give us y of 90, or the life expectancy of someone born 90 years after 1930. And this will be equal to 60.1 plus 0.356 times 90 minus 0.00162 times 90 squared. And plugging that again into our trusty calculator, we get that this life expectancy should be about 79.018. Again, we have 3 significant digits for each of these guys here, so we want to round this to 3 significant digits. So that'll just be these first 3 digits here. So rounding this up to there would just give us the 79.0. And so that 79.0 is the life expectancy that this model predicts in 2020. Now we can try to check our work by looking at actual real data here, because 2020 actually already occurred. And if we check out the CDC website and look at the life expectancy in 2020 for someone born there, we actually get that the life expectancy is only 77.3, which is actually less than this value here. And if you look at the trends in the table, you can see that life expectancy consistently goes up. And this actually goes down even from the 2010 time. Now, if you think about it, you might be able to see why the model failed to actually get a good number for that. Think about what happened in 2019 and 2020. That might have affected how long someone might live. COVID-19. So because of the higher mortality rate due to the COVID-19 pandemic, what we might have predicted with this model, which could not have taken into account the fact that there would be a pandemic in 2020, this model would ended up getting it wrong. And that's it for our tutorial on how to do a few problems of this type where we talk about functions and their graphs. We'll see you next time on trigonometry.